Okay, so today we're going to be learning about the fast way, the trick, the shortcut that I've been discussing for the last, I don't know how long, telling you that, guess what, guys, we're building towards something, and how important everything was up to this point was just laying that foundation for you. So today is really the crux of it all. Integrals actually, it's just quite incredible what Riemann discovered. When Riemann started looking at those summations, those equations that we have been solving and that I gave you in the very beginning of this, well, the chapter before this anyway, some of you have already noticed there's a pattern that goes on between those summation equations. Looking right at the first one, summation of 1 is n. The second one, summation of k, is 1/2 n squared. And as you can see in this slide here, you can see how I've almost highlighted those first terms. There's a relationship between that equation and the integral itself, and actually what that summation amounts to. We talked about the fact that those first terms are how we get the exact area. That's how we get it. And these other terms that are here in the gray are your error terms. That's what these all represent. So if I want the exact area, and as I discussed last week, that's what that symbol means. I want the exact area. Then all I really care about is those first terms. So what if I asked you then, what would be sigma k to the 5th? What would that one be? Great. I'm hoping that that's what you came up with, 1/6 n to the 6th. And I could keep going. We could do the summation of k to the 6th. And that, of course, would be 1/7 n to the 7th. And summation of k to the 7th. We could go forever. What do you notice is the relationship? For those of you sitting there not sure what's going on here, I want you to see if you can figure out what is the relationship between the one that I want and its result. How could I go from point A to point B? How could I get that readily? So if I asked you, and to write it even using this notation, I would like the integral, or the sigma, of, we'll even use k to the 10th. What would that look like? How would I come up with that answer? I actually want you to take some time here. If you're listening to this video at home, then I really want you to take some time. Pause, think through this. And I know that's asking a lot because some of you don't even want to do that. But I really want you to think about how would you get from point A to point B without having all the intermediate steps. It's not just that these are going up by 1 to go from n cubed into the... There's a relationship between this and its result. Every single time, what do you have to do? The first thing you should notice is that the power goes up by 1. So that would be k to the 11th. Or rather, in our case, we're using n's, so n to the 11th. And then what do you notice about the fraction before it? Dividing by that same power. That's what you're doing every single time. I know many of you would write this as n to the 11th over 11. That works too. That is, in essence, the integrals. Now, obviously, it'll get more fancy as we go through. But if I want to do an integral, I can actually find the exact area right away. I wouldn't even need much more than that. It's crazy, even when we have these expanded equations, how much easier this is. Riemann figured this out pretty quickly. And as you recognize how much faster this is, you're just going to be blown away. And you're going to be really mad at me and how much I made you do last chapter. Sorry about that. Not really, though. Okay, so I have the integral. That's what that says. So speaking in math terms, integral of x squared. Recognize that form. Here's all you have to do. Now, this is crazy. This is the fast way of doing it. Hopefully you recognize that what's happening here, and I'm actually going to do this all right in the same step here, that we can recognize what that equation is going to be right off. And what's more is, I know that this is going to use 1/3, and I'm going to use x, just so we keep it consistent with the letters there, x cubed. If I was to show you the long way, the way you've done before, in fact, I think I did this question for you a couple days ago when we did it in class the other way, where we were just using the first terms. You can see we just need to evaluate this from 2 to 5. This is what calculus does. This is everything. This is the shortcut. This is all of it in a nice little neat package. So once you recognize what that integral is in terms of x, Now all I have to do is I go like this, 1/3. I'm going to put that on the outside, just like you would have before. I'm going to take the highest term, if you remember, minus the lowest term. Check that out. That's actually the answer. We'd have 1/3. That would be 125 minus 8. 125 minus 8 is 117. So that's 1/3 times 117. When you divide, you'd get 39. That is the final answer. Maybe you don't believe me. Well, let's take a little bit of time here. I'm going to do this in pink here, the old way. That would be 3 over n, right? Sigma. That would mean I'd have to do 2 plus 3k over n squared. So just to write all that work out, I'd get 4 plus 12k over n plus 9k squared over n squared. Rolling down here a little bit, give myself some space, 3 over n. And now I'm going to have 4n plus 12 over n, and I'll even do as much as what we did last week, the 1/2 n squared. 9 over n squared, and I have 1/3 n cubed. Not doing the other terms because I want the exact area. So I have 3 over n on the outside. I have 4 plus 6, right? Because that's what 12 divided by 2 is. There's your 6. So 4 plus 6 is 10. Plus 3, that'd be 13n. And what do you know? You get 39. No coincidence there. Same exact answer. And Riemann basically saw this so that no longer did he have to go through all those painful Riemann sums and expansions. He actually, of course, they didn't call him Riemann sums because, well, he's Riemann. That'd be like me saying Madison sum. As you're doing this, the beauty of the shortcut here is I can take even these other equations, and I'm about to erase here. So I can do this next equation even faster. Again, it's split into 2 parts, so this does become kind of tricky. So understand that this has its component, and the 4 will have its part. So x, when I do the integral of that, think about it, it's going to go up a power, so it becomes x squared, and we divide by that new exponent. That's really the rule. Plus, now you might look at 4 and think, wait a minute, how do I go up a power? Well, remember that that's really 4x to the 0. So when I go up a power, it actually turns into 4x to the first divided by my new exponent. What's the new exponent when I go up 1? It's 1. So is that necessary? No. Really what you later learn is that you don't even put that on there at all. You literally just leave it as 4x. It just adds that x to it. Now we're going to evaluate from 1 to 5. Okay. Now watch how I do this shortcut way. I say shortcut way because it avoids fractions all along the way. So I have 5 squared minus 1 squared. If you did the 1/2 at the same time, you would have had 25 over 2 minus 1 over 2. Is that terrible? No. It can get kind of messy. I'm not going to lie. And then I have 5 minus 1. Notice these are always subtracting. Always subtracting. Always. If it's a negative number, then it would be minus and a minus. So there it would make it plus. But it is subtracting between those values. So 25 minus 1, hopefully you can do that in your head. That's 24 divided by 2 is 12. And then I have 4, and 5 minus 1, of course, is 4. So I have 16, and together makes 28. And that's your answer. That's your exact area between 1 to 5. Pictorially, that's a line, and so you could have done a triangle, x plus 4, so that would mean crossing here at 4 and negative 4. And if I wanted from 1 to 5, this area here, we would do the area of the triangle and the large triangle here, and then subtract off that piece, you'd get 28. That'd be another way of doing it. All right, let's do one more example here. And I think that's all I have today. So let me just do one more. If you want to try and do this on your own at this point, I would suggest maybe you pause the video. Go ahead and try this. If I was teaching you in class, I probably would have you at least start this by saying to you, okay, I want you to right now on your own paper, tell me what would this be, what would x squared be in that new integral form. So now go ahead and raise that by a power and divide by that new exponent. And so if you're doing this at home or you're doing this in class while listening to this, you can go ahead and hit pause. And I want everyone in the room to go ahead and try to solve that one first. Okay, and so if you are just coming back, hopefully this is what you got. You want to go up a power, so it's x cubed, right? And it'd be 1/3 x cubed. You divide by that new exponent, plus that becomes x squared. And so I have 4 divided by 2. Hopefully you can simplify that in your head. And then plus, it's just going to be 1x divided by 1, right? Because that would, x would now go up to the first power, and that's how that looks. I'm going to evaluate this from -2 to 1. Okay, so I have 1/3. Again, it's the highest one, 1 cubed minus -2 cubed. Then I have 2. I have 1 squared minus -2 squared plus 1 minus a -2. Okay, back to your math here. 1 minus a -8 makes that plus 8. I have 1 minus 4. And then I have 1 plus 2. So I have 9 divided by 3 is 3. I have -3 times 2, so that's a -6 plus 3. Gives me 0. You might think, how can that be? Well, remember the integrals are the area above minus the area below. And so the area above and the area below must be exactly the same if I was to look at that graph. And so that is how you do integrals the fast way. Feel free to replay the video as many times. I will have this link to my website, so if you do want to see this later, you certainly can.